All right, lesson 6.1, slope fields and Euler's method. That's how you pronounce it. A slope field is a graphical representation of a differential equation. So I want to look at example number 1. You have a differential equation, a derivative equation, and negative x over y. And what we're going to do is draw little lines of that slope on the graph. So at 3, 2, so if I go 3 to the right and 2 up, I want you to see the slope would be negative x over y. So that would be negative 3 over 2. And if you look here, 3 to the right and 2 up, that's a little slope where you went down 3 and to the right 2. Negative 1, 3. Remember, it's the negative x value, so it becomes positive 1 over 3. So if I go to negative 1 and 3, you can see I went up 1 and over 3. Here, again, negative x makes it positive 2 over negative 1 or negative 2. And if you go to negative 2, negative 1, you can see that's a steeper slope of negative 2. Kind of like you'd had a mini slope where you go down 2 and to the right 1 to create a little mini-me line. 2 and negative 2, so it would be negative 2 divided by negative 2, and that answer would be 1. So at 2 and negative 2, right there, we would draw that. So this is like up 1 over 1, just a little line that looks just like that. And then it says, why can't you find slopes at 0? And the answer is, at 0, the derivative is undefined. In example number 2, I have the same one. For each remaining marked one, can you find the slope of each one, going like one at a time? So, however you want to find this, start with 1, 3, and see if we see the pattern here. Sorry, 1, 2. So that would be negative 1 over 2. So like, picture being able to go down 1 into the right 2 and then draw a little line from that. Here, it would be negative 1 over 3. And if you have to write it out, negative 1 over 3. So if I go down 1 and to the right 3, just want you to notice that it's going to be a little flatter at negative 1, 3 than at negative 1, 2. So it's a little comparative. Here we have 2, 2, so that would be negative 2 over 2, which is negative 1, so I draw a slope of negative 1. Here I have 3, 3, that's also a slope, and what I recognize with the pattern of negative 1, that this whole diagonal has a slope of negative 1 all the way down. So whether it's 2, 2, 1, 1, and so on, here, same thing. This whole diagonal has a slope of negative 1. If I look at the other diagonal, so if I go to negative 1, 1, notice that the negatives here become positive x. So that's 1 over 1. All of these slopes in the diagonal is going to be 1. All the way there. All right, what points are left? So negative 2 and 1 would be positive 2 over 1, which is a steep. Here, negative 3 over 1 becomes positive 3 over 1, which is even steeper. Here, negative 3 and negative 1 becomes positive 3 and negative 1, so it's steep but a negative slope. Here, negative 1 and negative 2 becomes positive 1 and negative 2, so they go down 1 and to the right 2. And draw your line. This would be down 1 and to the right 3. This is going to be negative 2 over negative 1. So that's positive 2. This one's going to be positive 3. So I'm mentally going through this formula with each point. So 3 and 2 would be negative 3 over 2. So I count down 3 and to the right 2. Sorry, positive 3 over 2. Sorry. So count up 3 and to the right 2. and draw it. Did I leave anything empty here? All right, so now I've completed the slope field. Takes a little bit of time. In example 2, you made it known and you made a slope field. So starting at point 0, 1, draw a solution. So I'm going to change colors. So starting at 0, 1, draw a solution. And so I want you to notice the slopes are coming down to the right. But once it's here, they're going to be undefined at each one. The next one is at your solution curve must represent a function, so I can't go underneath and make a circle, whose domain is the largest possible open interval containing the given point. Sketch a solution curve through -1, +1. So if I go through -1, +1, so I can see what direction it's going. It's going up, and then here, if you see a horizontal tangent line, it's a turning point. And then follow the flow of the slopes. And that's through -1, 1. And then one more at 0 and -3. So find 0 and -3. There's a turning point there. And then follow the slope of it. And once it's undefined on that axis, so the slope is undefined there, then we draw holes where it's undefined. And again, follow the flow, turning point, and follow the flow. And you just drew what's called a slope field. Now, we're going to solve this differential equation. So we just solved it by graphing it. Now we're going to solve it algebraically. So it's what we did before, last unit. We're going to multiply everything by dx. And then I'm going to multiply by y. And then I'm going to integrate this. So on the right side, it's y squared over 2. This is -y squared over 2 plus c. I can multiply everything times 2. And then I can make and change this to a different constant. So I have y squared equals -y squared plus that constant. And then when I square root this, one answer is going to be positive in the square root of -x squared plus the constant. Again, it's going to be plus or minus, and it's the square root. And the second one's going to be negative. And the key, just like last lesson, it's the y coordinate that tells me whether I use positive or negative. So find the particular solution through 0, 1. So I'm going to use the positive one. I'm just going to use it up here. So I'm going to plug in 1 for y and 0 for x, and see that the constant is equal to 1. And then I'm going to use the positive one because the y coordinate is positive, so it's y equals the square root of -x squared plus 1. And then the second one is -3, so I'll still go here. 0, -3, so plug in -3 for y and 0 for x. And then when you solve it, the constant is equal to 9. But because the y coordinate is negative, we use the negative one for that one. These are actually semicircles, both the top and the bottom semicircle. All right, turn the page. In example number 5, there's a differential equation there, 1 over y. It's really nice when there's only one variable, because then I can just go y values by y values. So in other words, I can go row by row. So at 0, it's undefined. At 1, it's just 1 over 1 all the way across. So this whole row, y equals 1, and I only need the y value. So 1 divided by 1, this whole row has a slope of 1, and that makes it much easier to complete it than having two variables. The next one, y equals 2, we go up 1 and to the right 2. So it's just a little flatter. And then the next one is y equals 3, so we go up 1 and to the right 3. And this one's like flatter still. try your best to do parallel lines going across. And then y equals -1. This one's undefined, right, when y is 0. So -1, down 1 and to the right 1. Y equals -2, which is down 1 and to the right 2. Just do little dots if you need to. And then try to create parallel little lines as you go across. And then y equals -3. So again, go down 1 and to the right 3. Excellent. You just drew a slope field. Now, we're going to graph a solution through the point -2, -1. So find -2, -1. Recognize it curves up this way, and there's a hole there where it's undefined. And then it curves this way, but it kind of flattens out as it's going this way. So there's like the curve there. It's not exact. It's kind of a flow and a feel, and get a sense of it. 2, 2. Find 2 and 2. So I can see how it's flowing this way, and then I can see the same idea in terms of how it's flowing in that direction. Now solve the Diffie. So I'm going to write dy by dx equals 1 over y. Multiply by dx, and then multiply by y. Oops. So I multiplied by dx, and then I multiplied by y, and now I'm going to integrate it. So that's y squared over 2. You don't see it, but that's a 1. So integrate 1, it's x, and then plus c. I'm going to multiply by 2, and then I'm going to change out this constant. So we have y squared equals 2x plus c2. And then when we solve it, it's going to be positive or negative. So if it has a positive y value, it's going to be the positive. If it has a negative y value, it's going to be the negative. All right, write as functions what we just did. So I'm going to plug into here. So I have -1 for the y coordinate, and I have -2 for the x coordinate. And then I'm going to solve it. So I'm going to add 4, so I get the answer 5. So the equation would be, because the y coordinate is negative, we go negative square root of 2x and then plus 5. That's one answer. And then the other one, I'm going to plug in 2, 2. So that's 4 and 4. So when I subtract, that answer is 0. So the equation, because it's a positive y value, I use the positive, and it's the square root of 2x plus 0, or just the square root of 2x. All right, next example. If you have a slope field, can you match it up to the derivative equation? So which of these equations below matches the slope field shown at the right? And so is the derivative just x and so on? And so it's helpful to understand that when y equals 0, the slope appears to be 1. So at y equals 0, the slope is 1. So when y is 0, the slope is 1, or the y is 0. So this is definitely not right. The slope is the x value, which changes. The y at 0 would be x. This one, if y is 0, the slope is 1. And here. So it's helpful to find an attribute that you see on this and then test it to see which one actually works. So when y equals 0, if the slope is 1, if I plug in 0 for y, the answer always is 1. That's not true. That x value changes, the y value changes, and so on. This is the only one that fits. In example number 7, you're given an actual equation of it. This isn't a differential equation, but the equation, but this is still the derivative. So let's say I draw a solution, because I think that would be helpful. If I draw a solution in terms of what it looks like, what does that picture look like? And that would be helpful. So it looks like an exponential, but it's a decreasing exponential. So if I was going to guess, it looks like a decreasing one, which is e to the negative x. That's what the picture looks like. It's definitely not e to the x because it's rising. Negative e to the x would be below and have a different curve to it. It's not a logarithm. And so this is the one in terms of knowing your picture, in terms of what it matches. All right, turn the page. All right, this is now, that was actually an AB topic. This is a BC topic. It's called Euler's method. Oh, and look at that. I kind of drew into it a bit. Here's another way to do a solution for a differential equation using a chart. And so what we're going to do is, you're given a diff EQ, so the derivative is the y value. And so we're going to start here. A starting point is at 0, 1. So we're going to put in 0, 1. The derivative of y, of d dy is just the y value, which is 1. And then to find the change in y, we're going to take the slope, which is the derivative, times the change in x, which is 0.1, and get an answer. So 1 times 0.1 is 0.1. And so we have a starting point which is at 0, 1. Now here it becomes interesting. The x values are increasing by 0.1. So this is 0.1. The y value is now increasing by 0.1. So 1 plus 0.1 makes it 1.1. And now I find that on my graph. So find 0.1 and 1.1. Now, the derivative is the y value. So now the y value is 1.1. To find the change in y, we take the slope, which is 1.1, times the change in x, which is 0.1, and then we multiply this together. And that's 0.11. Now the change in x is 0.1, so this is now 0.2. I take this answer and I add it to the y value. So I take this answer and add it. This is the change in y now. It was this, but now the change is 0.11. So that's now 1.21. So there's my point. So 0.2 and 1.21. The derivative is just the y value, so there it is. And then to find the change in y, we take the y, the slope, which is 1.21, and multiply it times the change in x, which is 0.1. And then multiply those two together, and you get 0.121. And again, I'm going to add this. So this, I'm just going by the change in x. So I just keep going 0.1, 0.1, 0.1. This answer gets added to the y value, and I get 1.331. And then find 0.3 and 1.331. There it is. And then you can draw, and then that's another way to do a solution. That's called Euler's method. In example number 9, dy by dx of y, solve it algebraically. So we're going to multiply by dx, and then I'm going to integrate this. So that's y. This is, oops, I got to separate the variables. So we're going to divide by y, and then integrate. So 1 over y is ln. This is just x plus c. To solve for y, write it as an exponential. And instead of plus c, I multiply. I go plus or minus. And then I'm going to replace that with a new constant. And here it is. And then I'm going to put in the 0.01. So if I put in 0 for x and 1 for y, e to the 0 is 1, so y is, or c is 1. So e to the 0 is 1, and it's equal to 1. Divide, c is equal to 1, if I plug in the points. So the equation I'm looking at is y equals just e to the x. That's all I'm looking at in terms of it. So this is really like concave up. And then if I plug in with my calculator, at 0.1, the answer is 1.105. Plug in with my calculator. If I plugged in 0.2 with my calculator, the answer would be 1.221. And you can compare like the answers that I got this way compared to doing it this way, and then plug in 0.3 is 1.350. So these are the actual values. This is estimating using Euler's method, and you can see how accurate it is in comparing it. All right, let's look at number 10. We're going to use Euler's method again. The particular solution of this DiffEq passing through 0 and 0.5. So 0 and 0.5. The derivative is x subtract y. So whatever the x value is, subtract y. So this is negative 0.5. And then the change in y is the derivative, which is negative 0.5, times the change in x, which is 0.2. So that's negative Sure I'm doing it right. So that's negative 0.1. And now the x is changing by 0.2. So I add 0.2. The y is changing by negative 0.1. So 0.5 subtract 0.1 is 0.4. And again, this is the rule. X subtract y. So 0.2 subtract 0.4 is negative 0.2. So then I take negative 0.2 and multiply it by the change in x, which is 0.2. And that gives me negative 0.04. That's gonna change the y. The x is changing by 0.2. So this now is 0.4. Take 0.4 and subtract 0.04, and you get 0.36. The derivative is x subtract y. That gives me 0.04. And again, I take that answer and I multiply it by the change in x, which is 0.2, and that gives me 0.008. I'm going to, again, add 0.2 to the x value, and then add 0.008 to the y value. And then I'm going to take those values and come back here. So 0, the answer was 0.5. At 0.2, the answer was 0.4. At 0.4, the answer is 0.36. And at 0.6, the answer is 0.368. Which is a little bit higher, right? It's like we have a little turning point there. And then connect this together. In example 11, so what's the approximation at 0.6? The answer is 0.368 using Euler's method. All right, sketch a solution of the DiffEq, which we just did, x minus 1, y, through this point. So here's a slope field of that. Find 0 and 0.5. And if I would sketch it, it would kind of come up just a little bit, right? And if you look at the two and compare them, you can see how the pictures are similar, right? Do the two graphs coincide? Are they very similar? And the answer is, of course, is yes. And that's it. So, Mr. G Math over and out. I know this is brand new. We're going to practice it now for our assignment. Till next time.